Silver is often described as a precious metal, but the numbers that now define it are industrial. In 2024, global industrial silver demand reached 680.5 million ounces, the fourth straight record year. Within that total, electrical and electronics alone accounted for 460.5 million ounces, and photovoltaics accounted for 197.6 million ounces. At the same time, the market recorded another annual structural deficit, with demand exceeding supply again. When a metal becomes essential to power grids, vehicle electrification, solar expansion, and high-density electronics, its price story becomes secondary to its allocation story. Who needs it, where it is used, and how quickly supply can respond. The strategic question is not whether silver is important. The data already answers that. The strategic question is how silver's physical properties force it into parts of the economy where substitution is technically possible but rarely frictionless, and often slow because it must pass engineering standards and reliability testing. Silver is the best electrical conductor of all metals and among the best thermal conductors. In practical industrial design, that combination matters, because modern systems push electrons and heat through smaller spaces at higher speeds and higher duty cycles. As devices shrink, voltage margins narrow, and reliability requirements rise. Silver's role in strategic use begins in electronics, because the modern economy is electronics embedded inside everything: the grid, communications, vehicles, industrial automation, and defense platforms. The 460.5 million ounces attributed to electrical and electronics is not one product category. It is diversified usage at scale. In consumer electronics, silver appears in conductive pastes, inks, and adhesives, in switches and membrane circuits, and across printed circuit assemblies where stable conductivity and reliability matter. In industrial equipment, silver appears in contacts and relays that must handle repeated switching cycles without resistance buildup. In the energy system, silver appears in connectors and control modules that must function in high-load environments, where failures are expensive and sometimes dangerous. These uses are often small per unit, which makes them easy to ignore, but the scale is created by volume across billions of components. When a metal is used as a thin layer, a paste, a contact surface, or a conductive pathway, the arithmetic is not one device. It is global manufacturing output. This is why silver's strategic profile can rise even when engineers pursue thrifting, because throughput rises faster than reduction per unit. Photovoltaics is the second anchor of strategic use, and it changed the conversation because it links silver demand to infrastructure build-out rather than consumer replacement cycles. Photovoltaics demand was 197.6 million ounces in 2024, inside the broader electrical and electronics category. That number ties silver to the energy transition directly. Solar is not a niche consumer choice. It is a grid-scale input added year after year, and each wave of capacity pulls materials through supply chains that include silicon, glass, aluminum, copper, and silver. Solar cells have historically used silver in conductive pastes for metallization, forming the pathways that collect and move current. The industry has reduced silver loadings per cell, and that progress is real. But total demand depends on the balance between per-unit reduction and total unit growth. When capacity additions hit new records, total material demand can remain large even if silver per cell declines. In 2024, new solar capacity added in China was reported around 278 gigawatts, a scale that helps explain why photovoltaics remains a structural driver even during ongoing thrifting. A third pillar is vehicle electrification and the broader electrification of systems that used to be mechanical, analog, or hydraulically controlled. Electrification is not only battery packs and motors. It is power electronics, sensors, controllers, and higher density wiring and contact systems distributed everywhere. As vehicles add driver assistance, infotainment, power management, and safety control units, the count of electronic modules rises, and with it, the need for reliable contacts and conductive materials. Silver is used in contacts and circuitry because switching reliability, corrosion resistance, and conductivity affect failures. The strategic aspect here is not a single headline about EVS. It is the architecture shift. Physical systems now depend on complex electronic subsystems that are expensive to service and costly to fail. That architecture is also visible in grid infrastructure, where investment pulls a wide range of contact materials. Another large underexplained category is brazing alloys and solders. In 2024, brazing alloys and solders accounted for 51.6 million ounces globally. This is strategic because it sits at the boundary between manufacturing and reliability, where joining quality affects durability under vibration and thermal cycling. In refrigeration and HVAC systems, industrial piping, electronics assembly, and specialized manufacturing, brazing alloys can determine performance over long life cycles. In high-performance applications, including aerospace supply chains, material choices are constrained by safety standards and qualification requirements. There are additional strategic uses that rarely make headlines but matter for critical systems. Silver catalysts are one example. Silver is used as an industrial catalyst in chemical processes, including ethylene oxide production, a building block for plastics, detergents, and industrial chemicals. Catalyst demand behaves differently from electronics demand because it depends on installed industrial capacity and replacement cycles. When new chemical plants are built or expanded, catalyst loads can rise, and when capacity is stable, replacement cycles determine consumption. This ties silver demand to industrial base expansion. The most visible strategic framing emerges when national policy treats a material as security relevant rather than merely commercial. In late 2025, the U.S. Department of the Interior added silver to the U.S. critical minerals list, shifting the policy lens towards supply chain vulnerability and essential use. That designation does not change silver's physics. It changes how governments categorize dependence and disruption risk. It also aligns with a basic dependency visible in trade flows. The U.S. relies heavily on imports for the silver it uses, which matters when silver is embedded in electronics and energy systems. To understand why strategic silver is not a slogan, it helps to separate demand into discretionary and non-discretionary at the system level. Jewelry and silverware are real demand categories, but they are not what makes silver hard to replace quickly in modern manufacturing and infrastructure. Industrial demand is embedded in systems with long qualification cycles and high reliability requirements. If an industrial process needs a conductive paste that meets performance specifications at scale, changing it is not a simple swap. It can require redesign, retesting, retooling, and sometimes regulatory approvals. A material does not have to be physically scarce for strategic behavior to appear. It only needs to be difficult to substitute quickly at the exact nodes where it is required. When demand is distributed across many nodes, shortages do not have to be total to be disruptive. They can be localized by form and purity. This is why strategic use becomes a story of processing and fabrication capacity, not only mine output. Mine supply is critical, but refined product availability and industrial form supply can be the bottleneck that shows up first, especially for powders, pastes, high purity forms, and specialized intermediates. Market deficits matter even if they look smaller than total demand because persistent deficits compound. In 2024, the structural deficit was reported at 148.9 million ounces. Over 2021 to 2024, the combined deficit was reported at 678 million ounces, roughly equivalent to about 10 months of 2024 mine supply. The strategic implication of repeated deficits is not that the world runs out of silver in a literal sense. It is that inventories and above-ground stocks become more important in balancing the market. As deficits persist, the system leans more heavily on existing stocks and recycling flows to fill the gap. That shifts attention toward where inventories are held, what forms they are in, and how quickly they can be mobilized into industrial supply chains. Industrial users do not typically want random bars. They want specific forms that meet manufacturing requirements. And converting metal between forms depends on refining and logistics. Recycling is another strategic layer because it affects supply elasticity. Silver is recycled from electronics, jewelry, silverware, and industrial scrap, but recycling cannot be turned up instantly because it depends on collection systems, processing capacity, and product design. Dispersion across billions of devices makes recovery harder. Industrial scrap can be easier to recycle because it is concentrated and traceable. End-of-life consumer electronics can be harder because it is dispersed. This matters because strategic demand growth in electronics and photovoltaics increases the relevance of manufacturing scrap recovery and high-efficiency refining capacity. The supply story is also shaped by the economics of silver mining. A significant share of silver is produced as a byproduct of mining other metals like lead, zinc, copper, and gold. That structure limits how fast mine supply can respond to silver demand because expansion decisions depend on the primary metal's economics. Strategic demand growth colliding with constrained supply elasticity is one reason deficits can persist. It also increases the relevance of policy and investment in refining and recycling capacity. Even without policy changes, long-duration investment themes like electrification, data infrastructure, and solar deployment can keep demand elevated. Technology demand has added another layer through the AI-driven expansion of computing and data infrastructure. Growth in servers, networking equipment, power management systems, and AI-enabled consumer electronics expands demand for conductive materials. At the same time, data infrastructure expansion increases demand for grid upgrades. Military and defense demand is often discussed dramatically, but the verifiable framing is overlapped with advanced electronics. Modern defense systems rely on high reliability electronics, communication systems, sensors, and power management. Silver's role is distributed across contacts, connectors, and assemblies that prioritize performance. The strategic relevance is not that defense dominates total demand. It is that defense competes for the same high-quality materials and manufacturing capacity used by civilian sectors. When a material is used across both civilian infrastructure and defense supply chains, supply disruptions can create allocation questions with strategic consequences. The same logic applies to communications infrastructure. Telecommunications networks and data centers rely on stable conductive performance. Silver's industrial footprint includes components that sit inside these networks. Strategic use is therefore not only military, it includes systems essential to economic and national security. One way to frame this is by comparing domestic use profiles with global industrial categories. U.S. use estimates for 2024 have been published with large shares in investment bars: electrical and electronics, photovoltaics, coins and metals, brazing and solder, and other industrial uses. Industrial categories represent a large share. That split shows why strategic demand dynamics are not abstract. They are visible in a major economy's usage breakdown. It also highlights why silver demand can be resilient across cycles. Industrial and investment flows can move differently, but strategic use is anchored in industrial demand tied to infrastructure and technology build-out. Demand categories also differ in how they react to price. Higher prices reduce some consumer demand quickly. In industrial markets, higher prices often trigger engineering efforts to reduce loadings rather than immediate cessation because products still must be manufactured. Adjustments often come through thrifting and redesign. This is a key nuance for photovoltaics. Progress in thrifting and substitution can reduce silver per unit, but total ounces can remain high when unit volumes expand quickly. Strategic demand dynamics therefore depend on trajectories, not a single snapshot, because the market is shaped by both per unit change and unit growth. Geography adds another strategic dimension. Published demand breakdowns show East Asia as a large share of global industrial fabrication, consistent with the region's central role in electronics and solar supply chains. When manufacturing and processing are concentrated, logistics, trade policy, and supply chain decisions matter more. The critical minerals designation fits into this context because it reflects a recognition of vulnerability. For silver, the strategic question becomes not only how many ounces exist, but how many are available in the right form, at the right purity, in the right place, under stable trade conditions as industrial demand climbs. The final piece is that silver demand is increasingly tied to long-cycle investment categories. Grid upgrades, renewable deployment, electrification, and technology infrastructure are influenced by policy and capital expenditure cycles that do not reverse quickly. Even when macro conditions weaken, systems still require maintenance and parts. This does not mean industrial demand cannot slow. It means a large portion of demand is embedded in system maintenance and infrastructure expansion, rather than discretionary consumption. In that framework, silver's strategic role can be described without prediction. It is consumed where electricity and reliability are non-negotiable. The data show record industrial demand, sustained electronics consumption, photovoltaics as a major component, and repeated market deficits over multiple years. Silver is not only a metal held for price, it is a metal built into the hardware of modern growth. The conclusions are yours.